Just this, yes?
Yeah.
Yeah. Okay, y equals that to the power of y equals, oh, what was it, that?
Yeah, to the power of 3/2.
And they want to know the gradient at x equals 1/2 log 3. Right. So you know the formula dy dx equals dy du times du dx, yeah?
Yeah.
What's u here then?
1 plus e to the 2x.
Exactly, that's the inner function. And so we can think to ourselves, what's any function, what's anything to the power of 3/2? What does that differentiate to?
3/2 to the power of 1/2.
Yeah. And then, so you could say dy dx therefore equals the same stuff to the power of 1/2, times 3/2. Now that part of it there is what part of this formula?
dy du.
That's right. We've differentiated y, the whole thing, but as though the variable of differentiation were the whole of the inner function.
Okay.
So now we want to multiply by the derivative of the inner function.
2e to the 2x.
2e to the 2x, did you say?
Yeah.
That's right. You've got another little chain rule happening there as well, haven't you? But you've dealt with that by bringing the 2, by multiplying e to the thing by the derivative of the inner function too. So that's it, basically.
Okay. So when you put the 1/2 log 3 in.
Yes. Oh, I see. So that wasn't a problem. It was just subbing that in, was it?
Yeah, that was me.
Fine. So really, we've got 3 e to the 2x
Yeah.
root of that. We'll try again. Which equals 1/2 log 3. So 3, 2 times 1/2 log 3. Fair enough?
Yeah.
So far? 1 plus e to the 2 1/2 log 3. Okay, so far? So 3e to the power of what?
3, no. What? Log 3, sorry.
Sorry, say again?
Log 3?
Yeah. Carry on.
Do they cancel?
Yeah.
Okay.
Because what does natural log mean? It means the power you have to raise e to get 3. So if this is the power we have to raise e to, we get 3. You know, if that's the power we have to raise e to get 3, well, we're raising e to that power, so we're getting 3.
Okay.
So in the end?
Is it 27?
Oh, in the very end, or what? So what about this?
Is it just 3 to the power of 3? Or is it 3e to the power of 3?
You're not quite passing it. That simplifies to what? Are you clear on what e to the power of log 3 is?
No.
Well, what does log to the power anything mean?
Power you have to raise by to get
that.
Yeah.
Right. So in the case of Lynn, it's the power you have to raise e to get 3.
Okay.
But the power you have to raise, so what we're saying is, if you raise e to this power, this whole thing, you will get I mean, if log in general means the power you have to raise the base to get that number, this is saying this whole thing, the value of this quantity is the power you have to raise e to get 3.
Yeah.
So if we raise e to this power, we will get 3.
Okay.
So just, using the definition of a log, you can see, well, when we raise e to this thing, which is the power we have to raise e to get 3, well, then we're going to get 3.
Okay.
So this thing here simplifies to
3.
3.
Okay.
Okay. What's 2 to the power of log base 2 of 10?
10.
Yes. What's log base 2 of 2 to the power of 10? Well, use the form of words. What does it say?
Is it 10?
It's 10 again, because it's what this says, what we've got here is the power we have to raise 2 to get 2 to this power. Well, if we get 2 to this power, that power we're raising 2 to must be this power here, 10. Again. Okay. So you've got 2 ways in which e directly cancels Lynn, which is either this way round or this way round, which is also what?
3.
3. So you can just mechanically get in the habit as well. That's fine. It's fine if it's a habit, as if you use it consistently. So, these 2 cancel, or these 2 cancel.
Okay.
These 2 cancel, or those 2 cancel.
Okay.
Right. So finally, what do we get?
9.
Times?
2.
Yeah.
Okay.
Okay.
Yeah, okay. Thanks.
It's useful to be on board with all of that cancelling, especially when you've got exponential functions, obviously. Yeah.
Okay.
But like very often with those kind of differential equations where you end up with an exponential. Yeah. Well, I say those differential equations. still January, you might not have done those things yet.
We've done differentiation.
Yeah, but not differential equations quite yet, probably.
I don't know. Yeah, we might not have.
It's just, I mean, what's a differential equation? It's where you've got an equation with a differential or a derivative in it. So if you have dy dx equals x squared, well, solving that for x, you would integrate, wouldn't you?
Yeah.
And you would say y equals?
Third x to the power of 3.
You would indeed. Well, that's kind of solving a differential equation. So you do know about differential equations because you integrate where appropriate, right?
Yeah.
But differential equations in general, instead of, it's really where you're not lucky enough to be handed it on a plate like that. So you know, oh, well, if I want y instead of dy dx, therefore I want the integral of that instead of that. Because, have you come across something called implicit differentiation?
Yeah.
Right. And so differential equations in general are more like trying to reverse an implicit differentiation rather than an explicit one where you've got, because you had y as an explicit function of x, you have dy dx as an explicit function of x. But if you had an implicit equation where you had y, well, we could use this one. If you had y plus, I don't know, y squared, right?
Yeah.
Then if now you haven't got an explicit function of x, have you?
No.
You've got y as a function of x and y. Oh dear. Could we make y the subject here? Yes, probably with difficulty. But if you've heard of implicit differentiation, you know that you don't have to make get y as an explicit function of x in order to do the differentiation and find dy dx, do you?
Yeah. No.
So carry on differentiating this implicitly. What do we get?
2y times dy dx.
Well done. Splendid. And now, now you can get dy dx explicitly. Or maybe not straight away. Start solving for dy dx.
Right, what do you mean? Do I have to put y into the equation? Oh, well, no, I mean, sorry.
I mean, let's try and make dy dx the subject here, that's all.
So swap the, oh no, just get the 2y dy dx onto the other side, so minus it.
That's right. And then?
Take dy dx out. One minus 2y. And then x squared over 1 minus 2y.
Okay, so you know all about that.
Yeah.
That's how you differentiate implicitly. And the thing is, well, now we've done that, we could also integrate. Oh, no, we couldn't. Sorry. No, this is exactly the point. Here's a differential equation that you can't integrate explicitly. So that's the more general problem with a differential equation.
Okay.
But then on the other hand, having done all this, you can probably see how we might try and solve a differential equation. In this case, we can do it exactly like that. Oh, great, good. This was a happy accident. So how should we solve this differential equation? Even though we haven't got dy dx as an explicit function of x, because we've got a y in it, which is complicating things massively, isn't it? How on earth would we integrate that anyway? Even if that was an x, it would be a problem bad enough, maybe. But you never, you know, when you're integrating a function of x, you need a function of x, don't you?
Yeah.
So how can we integrate both sides of this so that we get y on the left-hand side and a function of x on the right-hand side, or even a function of y on the right-hand side? But how can we do it? We just don't know. But then we do, and I might as well, well, you know, might be introducing you to it, but on the other hand, you might have heard of it. This thing called separation of variables is what you'll be doing.
Okay.
Where you say, the problem is that we've got x's and y's on the same side. Let's bring this y expression over to the left-hand side. In other words, go back to that.
Okay.
But then you are ready to integrate both sides. Actually.
Okay.
I mean, yeah. What you would do, you wouldn't go back another step like that, probably. I mean, you could, but you wouldn't. What you would do generally is go from here and say, okay, what could that be the derivative of? No. You would say, okay, what if we think of y as an inner function? And now here we've got the derivative of the inner function. So we can imagine that we've come down from up here via the chain rule, spitting out the derivative of the inner function on the way. In other words, y is like u. So the whole function is like y, and then the y is like u. So here we've got dy du in effect, but it's confusing, and it's not your fault if that's totally confusing, because I'm calling, you know, I'm saying the whole thing is y instead of y is y. Have I lost you slightly?
No.
I mean, good. You can see that y is taking the function of an inner, playing the role of an inner function, which we usually call u, don't we?
Yeah.
And so dy dx is like du dx. It's what was spat out on the way down. Okay?
Yeah.
So what was the function of, what was the outer function? The function of y, which differentiated like this then? So what's the outer function here? If the inner function is y, what's the outer function?
dy dx.
Well, say again.
I don't know.
I'm thinking the outer function is 1 minus 2 of it.
Oh, okay. Yeah.
So what's the integral of 1 minus 2 of something?
X minus.
Yeah, but don't forget, when we use the chain rule,
Yeah.
we've got du dx here, but everything else is in terms of u. So it's in terms of the inner function. So now,
Oh,
so there's no x's here. What we're doing here is really integrating this with respect to y, with respect to the inner function.
Oh,
which is y. So what's the integral of this, all of this, 1 minus 2y with respect to y?
y minus y squared.
Well done. Exactly. So this, no, sorry. This we turn into this, which is now equal to just x squared. And then if we can, so what we've noticed, we've integrated with respect to y, but because of the chain rule, we've really integrated with respect to x, haven't we?
Yeah.
Because if we were differentiating this with respect to x, we would differentiate with respect to y, and then multiply by du dx, which is the derivative of the inner function, really, with respect to x.
Yeah.
So we differentiated with respect to x, really. So because we've got this inner derivative, this side is with respect to x. So just on the principle of balancing, we can integrate this side with respect to x. And this would be what?
Third x to the power of 3.
Yeah. Okay. And is that right? Yes. We end up back here, don't we?
Yeah.
Although we might not want to, we might think, oh well, y is more like being the subject here, and then we would try and make y the subject. But at least we found the integral of that differential equation, which needs separating because you've got the two variables, both variables on the right hand side. So you separate them out appropriately and then use the chain rule. And you might be taught little notational tricks, which are beside the point. Right, anyway, I'm just mentioning that by the way, why? Because I said that when you solve that kind of thing, you often end up with an exponential up here, and you end up trying to get to this kind of result. You recognize this kind of exponential thing?
Yeah.
And that often happens just owing to what it is you got on the right hand side here. My example wasn't correct for the exponential. But if you have an exponential here, the way it'll generally happen here, not because you've got an exponential on the right hand side, it's because you've got a fraction on the left hand side, and a fraction integrates to, if you've got 1 over something, that integrates to what? What does 1 over anything integrate to?
Is it log? Actually?
Yes, log of stuff. So if that's y, a function of y, you end up with that's a y or a function of y, you end up with log of y equal to stuff, and then that's why you get y equals an exponential as part of this separation of variables kind of differential equation.
Okay.
Is all I'm saying, by the way. Do you want to do some of them, or anything else in particular?
Don't mind. Yeah, we can do.
Might as well find one of those since I've gone into that much detail. Let's find some more of those. So find general solutions to the following differential equations. Give your answers in the form, in other words, make y the subject. So if we look at that, we'll Okay, so where should we start with that? It does seem to be the result of an implicit differentiation, doesn't it? Because just like here, when we made dy dx the subject, we found we had a function of y as well as x. So that seems to be what's happened here. So the question is, how can we kind of reverse that? Not go exactly the same path backwards necessarily, but how can we deal with it? Blue is in the name, don't forget. What's the name of the method?
Separating variables.
Separation of?
Variables.
Variables, yes, quite. So first of all, let's separate the variables and write what?
What, do you put them on different sides?
Yes.
Um,
Yes, it's literally separating so that we've no longer got the y's and the x's mixing on one side. Except for here, you might say this y and x is mixing, and actually that's the horrible, the bit I don't like, but I might as well teach you, I suppose. We separate these y's and x's as well, but.
So, is it?
But not yet. Just separate these, basically. Yeah.
Dy dx divided by 1 plus 1.
Yes, kind of. But what does that really mean? I mean, it looks a bit awful, doesn't it? That situation.
Yeah.
What's a nicer way of writing that?
Dy dx times 1 over 1 plus
Absolutely.
1.
Now, times dy dx. I would put that second, just because we know that that's going to be the inner derivative of a suitable inner function of this, which we're viewing as a composite. So we know we're working backwards through the chain rule.
Okay.
And as you know, my preference is to think of integrating as going upwards. So I'm going to drag that down there so that we can start. Now we're saying that's equal to what?
1 minus 2x.
So this is what we're integrating, solving. And we're trying to get to y equals stuff in terms of x, okay?
Okay.
And now we know we can get something like that. Not necessarily just y on its own straight away, but we'll get something to do with y, or something to do with. So we know we're saying our strategy is to say, okay, what's happened is the left-hand side has been differentiated with respect to x, and so has the right-hand side. So we're going to integrate both sides with respect to x to get up here.
Okay. Yeah.
So we could do the easy one first. We could say, okay, we know this is going to work now because it's a chain rule situation. Let's do the right-hand side first with respect to x.
X minus x squared.
Yeah, pretty similar, isn't it, to what happened before? But over here, now you have to recognize this as a reverse chain rule.
Mm-hmm.
So how can we see this product, because it is a product, isn't it, as a composite times the derivative of the inner function of the other one on the way down? What do we suspect is the inner function of the composite?
1 plus 1.
Yes, the whole of that, absolutely. In which case, what's the integral?
Y plus.
Well, forget about the 1 plus y in there.
Okay.
What's the integral of 1 over anything?
Log.
Of the thing.
Oh, okay. So log.
So it's log of?
Y plus.
Well, no, what is blob? What's the inner function, did we say?
Oh, 1 plus y.
It's 1 plus y. But then hopefully, if we imagine differentiating log of 1 plus y, what would we get?
1 over 1 plus y.
Right. We would if we were differentiating with respect to the inner function, with respect to u.
Oh, times dy dx.
Times dy dx, because that's the du dx bit, isn't it?
Yeah.
This bit is the dy du bit. Got dy du times du dx. Okay, except it's a function of y times dy dx, just to mess things up. But if we differentiate that, you see we get precisely this.
Yeah.
Okay. Well, in that case, but what have we differentiated with respect to get from there down to here?
Y. X, sorry.
No. I mean, if we say this is, I mean, what should we call it? Let's call it Z.
Okay.
What have we differentiated Z with respect to?
X and y.
Sorry?
I thought it was X.
Yes, good. So what have we, so we've differentiated Z with respect to X, haven't we?
Yeah.
And what have we differentiated the right-hand side with respect to?
X.
Yeah. So everything's cool. Yeah.
Okay.
We've integrated both sides with respect to X. But in a way, what's happened is we've pretended that we were integrating with respect to y here. But that's just because we knew we could do that because we had the derivative there.
Okay.
So what a lot of people do actually is they put an integral sign there, and then they bring that dx down to there, and they say, oh, look, isn't that lovely? I'm differentiating this side with respect to y, and I'm differentiating this side with respect to x. But that's not really what's happening, is it?
No.
I think it's better to understand that you're integrating both sides. Did I say differentiating when I meant integrating? Apologies if so. But you're not integrating one side with respect to y and the other side with respect to x. You're integrating both sides with respect to x. Yeah.
Yeah.
And you can check here by differentiating these and making sure you get those, which you can't if you've got those all over the place. I wouldn't do that.
Okay.
All right. So, but that's preference. Yeah, you know, you can do what you like. Well, you know, whatever works for you. So, one more detail up the top here. What do we need? What must we generally not forget when we're integrating anything?
Oh, plus c.
Yeah, but then we've integrated both sides, so perhaps we need oh gosh. So perhaps we need a c on both sides, do we?
Yeah.
The trouble there is they cancel, don't they?
Oh.
But then perhaps they're different constants anyway, because they could be anything on each side. So perhaps it's C there and D there. But then you don't really need a second one, do you? Because you might as well say the one over here is C minus D.
Okay.
So you don't need a constant on both sides.
Okay.
But you must put a constant on one side.
Okay.
Okay, now all we've got to do to get the marks here is get y as an explicit function of x. So we want to make y the subject now.
Okay.
So starting from here, log of 1 plus y equals, and this is what I was going on about in the very first place. So it's just as well we get to grapple with it now. Go ahead.
Would you put it to the power of e?
Sorry, say again.
Raise it all? No. Put it all to the no. I can't.
Yes, it's hard to say, isn't it? It's hard to say that way round. Put it all to the power. You know, that means the opposite, doesn't it? You're almost saying raise it all to the power of e. That's the opposite of what you mean. I know what you mean.
Yeah.
I've tried to say exponentiate both sides
Okay.
sometimes, but it doesn't really work, does it? I'm not sure if it's true either. Do an exponential of both sides. How about that?
Yeah.
So here, what do we get?
E to the power of x minus x squared.
Plus c even.
Yeah.
Which we could simplify to? Just only slightly. It's just that what we always do is pick this c out of it like this. And then we call e to the power of c, by convention, usually what letter? It's this a that you keep seeing cropping up in, you know, the standard statement of an exponential like that.
Okay.
And then, okay, we haven't just got kx, we've got something more complicated. By the way, instead of writing just that, we could also write what?
Don't know.
And now I'm not sure where this is going, but surely it's that. And then I was worried but yes, it does cancel. So why am I not cancelling there already? Why am I not? I mean, that's good, isn't it? And that is definitely e to the x all squared as well. So yeah, I don't know why this isn't obvious to me, but in the end, it's a e to what power?
-1. Oh no, no.
Minus x.
Oh, minus x.
But that's not that. What have I done wrong? I mean, if that's the same as that, then x minus x squared is minus x, and that's not true. Whoa, what am I doing wrong? But right. Do you know what I was doing wrong? Neglecting to put brackets there. And thinking that was the same as e to the x all squared. Oh, criminal. So it's that or that, but not what I was daring to suppose.
Okay.
Oh, phew. Right. Okay, next. Let's do, because it's practice all sorts of other things as well, isn't it? So even if it's looking slightly ahead, and what was ever wrong with that anyway. So dy dx equals y tan x. So we look at this, they say solve this differential equation. And what should we do?
Separate them.
And say?
Dy dx times 1 over y.
Yeah.
Equals tan x.
Also, if you put this one second, then you can do the notational bit if you like, but I wouldn't. Right. Then?
Integrate.
Integrate, that's right.
Log y.
Yeah. You see? Yeah, so but that is with respect to x, you appreciate that?
Yeah.
Because of the chain rule. Good. And then the right-hand side with respect to x. Do you happen to know the integral of tan x?
Is it log sec x?
Well done.
Well, yeah, I think it's.
Excellent. What have I forgotten?
Plus c.
Well done. Next. By the way, here's the trick. Just so that you don't have to worry about, oh, I had e plus c and then I'm just calling that a.
Yeah.
The trick is to just, instead of writing c here, write log a. And sort of 7 times out of 10, that'll help.
Okay. Exponentiate.
Yes, exponential of each side.
Y equals sec x plus a.
Y equals what?
Sec x plus a.
Ow! Ouch.
Oh.
Don't forget, you're exponentiating, if that is a word, the whole of each side.
Oh, e to the power of sec x.
E to the power of what?
Sec x.
What's the whole of the right-hand side?
Sec x plus a.
I thought it was log sec.
Does it not cancel though?
No, careful. This is where we have to be careful. That's why we're doing this, by the way, just to justify my, launching into all of this. It is relevant to what, the issue you were having there. Mm-hmm. So you must think of it as raising e to the power of the whole of each side. Yes, yeah. We're raising e to the whole of log y, okay, but we're also raising e to the whole of what on the right-hand side?
Log sec x plus log a.
Yes, and then carefully pick that apart. How? Oh, okay, that's a bit crazy. So y equals what? What happens when you've got a power as a sum of two terms? How can you expand that? For example, how can you expand x to the a plus b?
X to the a times x to the b.
Exactly. Do the same here.
E to the power of log sec x times e to the power of log a.
Yeah. Now what?
Sec x times a.
Exactly. Yes. Now that the e's and the logs do cancel, but notice you've got. I hope that's the opposite. That's not what you said. You did. Do you see the difference from what I hope you said? Apologies if I misheard you, and you were saying that all along. I thought you said what?
Sec x plus a.
Yes. So you see why it's times and not plus.
Yeah.
Because you must think of putting all of that as the power of e.
Yeah.
Put as a power of e is probably the easiest way to say exponentiate, isn't it?
Yeah.
So are we done? Yeah, because we've got the, we've added c, we've dealt with the unknown constant. So that's the unknown constant there in the a. Don't have to worry that there isn't a plus c. It's there really. So y equals a sec x. Well, let's. Okay, what should we do first?
Separate them.
Yeah.
Oh, are they not? Oh no, sorry. Is it 1 over y squared times dy dx?
Absolutely. Good.
Equals sine squared over cos squared?
Say again?
Sine squared over cos squared?
Yeah, quite. Which we might think, oh, that's tan squared, isn't it?
Yeah.
Tan squared not being, correctly on this, because you were good. I noticed you know the integral of tan. Well done. So we didn't have to do that from sine and cos, but we could have done by a backwards chain rule,
Yeah.
Have you integrated tan over x as sine and cos to
No.
get the log sec x?
No.
Because that was, in that case, that was a missed opportunity. We might be forced to do something similar here. I'm not sure. I'm really not sure how to integrate that. Blimey, sine squared over cos squared, it can't be that bad. It is that, isn't it? Yeah, definitely. The x is on, we've separated variables correctly. We probably know what to do. Let's do the left-hand side first, because that's easier on this occasion, apparently. Okay, go ahead with the left-hand side.
Log y squared.
Not this time, careful. That's why they were sneaky putting this in here while we were just getting used to integrating the left-hand side. And it is the general thing, yes. It is what you're generally expecting to see at least 50% of the time, that you end up with a log on the left, which is why you say log a for your constant on the right, yeah?
Yeah.
But not if it's, remember, integrating 1 over a square is different from integrating 1 over x. 1 over x integrates to log x.
Yeah.
but you wouldn't, but 1 over x squared wouldn't integrate to log of anything, would it? 1 over x squared, you would just say, oh, that's x to the -1
Okay.
that I'm integrating. And here you're just integrating, sorry, 1 over x squared would be x to the -2, I meant, didn't I? Sorry. And this is y to the -2, which integrates to?
Minus y, 1 over y.
-1 over y, yeah. So perhaps we're less likely to think of using log a instead of c in that case.
Okay.
I mean, you could use a, but you'd probably use c. Okay, so that is integrating with respect to what on the left-hand side?
X.
X. You might be pretending it's y, and you might like to, do sort of do the pretense by removing that dx and taking it over here and putting an integral sign and say, look, I'm integrating with respect to y on the left-hand side, which you virtually are, but I think you should be aware of the chain rule that's going on there. Now, how on earth shall we deal with this to just integrate sine squared over cos squared? Blimey. It's sneaky, isn't it? How
Do you have to
say again?
Do you have to rewrite them using double?
Yeah. Probably split it into a product. Probably, I'm thinking aloud. I don't know. I haven't worked this out yet, or it's probably something I should be aware of. But I'm just guessing that we try and turn it into a backwards chain rule, as in general, okay, what's the situation here that Sir is stuck on? Just an integration that we can't use partial fractions, so we've got to sort of tackle it as probably backwards through either the chain rule or the product rule. I don't know how much we've used that language yet. Backwards through the chain rule, backwards through the product rule.
Yeah.
Have I inflicted a lot of that on you yet?
Yeah, I think so.
Good. Anyway, so either way, whether it's a chain rule product or a product rule product, if it's a product rule product, then half of it's missing, because you know that the product rule, you need 2 products.
Yeah.
But if it's a chain rule product, it'll all be there, just like it was here. Like this was a chain rule product, wasn't it? This thing, which was a composite, times this thing, which was suspiciously like the inner product, not inner product, the derivative of the inner function of the composite. But it's not like sine squared is going to be like the derivative of cos squared. I mean, we could say sine is the derivative of the inner function if we didn't have another sign there. And of course, there's an easy fix. It is pre-processing. I said that it's not as though we could do partial fractions on it. But there's another kind of pre-processing that I should have flagged up before launching into backwards chain rule or whatever, which is Pythagoras, or just any old trig identities.
Okay.
Now, do you know what? Tell me Pythagoras.
What, in terms of sine?
Yes.
Sine squared plus cos squared equals 1.
Now, do you know another version of that? Well, for example, let's divide through by cos squared.
Oh, yeah.
Now what does it say?
Tan squared plus 1 equals sec squared.
Do you know that one?
Yeah.
Also, if you divide through by sine squared, what do you get?
Cot squared plus 1 equals cosec squared.
Exactly. Yes. So that's how we deal with that. In general, before I noticed what yes, the thing I should have been thinking of, apart from forgetting about trig identities, it's generally the right process. Think, can I pre-process it at all with partial fractions, but trig identities as well? I shouldn't have missed, and then start trying to pass it as a product rule or chain rule product.
Okay.
So try and be strategic. Just don't panic, because you never know what you might have forgotten like that. Right. Okay. So what we're really looking at here, since it's tan squared, can be rewritten as what?
Sec squared minus 1.
Yes. Indeed. Sec squared minus 1. Sorry, I was just confused. And do you happen to recognize sec squared as a derivative?
Is it tan?
Yes. Good. Well, I'm glad you've been doing enough differentiation and integration of trig functions to know that some of these are worth knowing, or just knowing that they exist and you can look at them up in the formula booklet as well. They're in there, but you're quite right. The integral of sec squared is tan. And the integral of 1 is?
X.
So we'll go from here. Minus 1 over y equals tan x, what?
Plus c.
Thank you. Good. Yeah. Now, how can we make y the subject?
Times by y and divide by tan x plus c.
Yes. What did you say? Times by? Yes. I mean, if we times by 1 and then divide by the right-hand side,
Yeah.
in other words, that would be just like saying to yourself, take the reciprocal of each side.
Yeah.
Is what I would. Indeed, it's the negative reciprocal. So y equals what?
Minus 1 over.
Yeah. Over what?
Tan x plus c.
Yeah. All of it, yeah?
Yeah.
So again, the constant ends up kind of hidden. It's not plus c in the end. Don't worry about that. That's where it is. And you've got y as a function of x.
Okay.
Time for one more?
Yeah.
They're not taking long, are they? So that's their fourth of those examples there. Of course, yes, we never found the value of the constant c. So you can see that in number 2 here, they're saying, okay, and here are some initial values, particular values, which enable you to settle the value of c, which you do just like you do for any equation, just by saying, for example, this is what's happening for these particular values of x and y.
Okay.
Will settle the unknown constant value, just like it does in a straight line. So what we're saying?
I don't know how you'd separate. Oh, is it would you write it as 2e to the x times?
Oh, you could do. Well spotted. You might as well, yeah. Let's say that means that dy dx equals 2e to the x what?
Is it divided by e?
And you have to do that as well, because we don't want x's on the left any more than we want y's on the right. So silly me. I was about to put it over e to the x minus y, and I wasn't even spotting the glitch there, which is fairly obvious. Oh, well done, yes. So we've got 2e to the x what?
Is it divided by?
Yes.
E to the y.
E to the y, well done. So we're going to say what instead?
E, oh no, yeah, e to the y times dy dx
Yes, indeed.
equals 2e to the x.
Okay. Now we're ready to integrate both sides with respect to x.
Which side first?
Sorry,
Which side are we doing first?
up to you. Pick the lowest hanging fruit by all means.
Sorry.
What are we differentiating with respect to on each side?
X.
Yeah. Well, do you know the integral of e to the x?
Isn't it e to the x?
E to the x, isn't it? So the
So
integral of 2e to the x is?
Oh, 2e to the x.
2e to the x.
Oh, okay.
A constant multiple just comes along to the right, doesn't it?
Okay.
Plus
C.
Plus c, thank you. Yes, good. What about here?
Is it just e to the y?
Yeah. E to the inner function will be dy du. And the derivative of the inner function, du dx, is dy dx. Great. And finally, make y the subject.
I don't know how you do that.
I mean, I'd rather not mess up my diagram. So we'll do it here. So, sorry, what?
Did you put login?
Put
Login somewhere?
Did you say log e? Natural log?
Log, yeah.
Take logs of both sides, yes.
Okay.
And what
So
do we
does
get?
that cancel them as well?
Sorry?
Does that cancel them as well?
Yeah. There's two cancels, isn't there, we were saying? That cancel.
Yeah.
Where you have log to a base of that base value raised to a power. And by the way, you could think, oh, I'm putting the 3 round the front and then I've got log, and you can see those cancel. You know that log of anything, log to base anything of the thing is 1. That's another way of doing that cancel.
Oh, okay. Okay.
So whichever way you look at it, yes. We're going to write what?
Log e.
Yes, log to base e of e to the y, but we wouldn't bother. We would just write y equals
2x.
Again, that's being impatient. See, remember what happened? here, where you were
Yeah.
hoping to say, you know, sec x plus a, and it wasn't, was it? You had to remember to put the whole of each side as a power of a.
Oh yeah, sorry.
Oh, sorry, hang on. Yeah, but that was the other way round, wasn't it? Yeah, but the same thing applies. The point is, whatever you do when you're balancing, you're doing it to the whole of each side, first of
Okay.
all. Then you might expand or split or something. But what did we do on the left-hand side? To the whole of the left-hand side, we took the natural log. So on the right-hand side, we're going to have
log to the x plus c.
of all of it. Yes, definitely need brackets there. And then by all means, look at that and think, well, can we split that? Can we expand that? And can we?
So just log to the x plus log c.
Tempting, isn't it? What are the log rules, though?
Oh,
Log AB expands to log A plus B. But what does log of A plus B expand to?
don't know.
Nothing really.
Oh, okay.
Nah. Just, you know, nothing interesting, nothing neat is going to happen. Log of a sum is log of a sum. Sorry.
Okay.
So that's it.
Oh, okay.
Right, leave it there.
Okay.
Is that all right? Anyway, that's that. Yep.
Yeah, fine. Yeah, thank you.